Okay, thank you for the nice introduction. So today we are going to see our work is skeleton-based cage generation guided by harmonic fields. So I will give you first a brief overview of the work. So the aim of our work is to build the cages for animation. Cages together with skeleton are the main structure used in the animation pipeline to deform a digital model. They are very different, starting from their shape to their functionalities. They are always used in combination to perform different kinds of deformation. Both cages and skeleton are used in several applications apart from animation. Skeleton are also used to as shape descriptor. While cages are very important in several topics, such as shape approximation, collision detection, and so on. Cages for animation are a particular kind of cages that should have a particular properties. They should be homomotic to the shape as the other cages. They should be external. That means that a cage should be an approximation of a bounding approximation of the input shape. It should be coarse. That means that as the lowest number of vertices possible. It must be intersection free. This is a mandatory requirement because it's due to the deformation method. If this constraint is not kept, the deformation will not work at all. And then it should be articulation aware. That means that the vertices of the cage should be placed in the area of the model that should be deformed. It should be bent. For example, if I want to bend the arm, I should have a ring of vertices in the proximity of the elbow. So, and a desired property can be symmetric, such as several characters built for animation are modeled in a symmetric way. So while we would like to handle this this goal, the problem is that the construction of the cage is a very tedious task and requires several hours from a skilled artist. It's not easy because there are several properties to be fulfilled and they are in contradiction each other. And usually the optimization of geometry is challenging around the highly concave region of the shape. So we will see a brief background of the related works. So there exist several related works to cage generation. They can be roughly categorized into categories: automatic approaches and interactive one. In the automatic approaches, we have the one based on mesh simplification, and the one based on visualization. These one are purely geometric and rely basically on the pose of the character. It's not possible to control exactly the location of the vertices, and as such, they are not very much animation aware. And we have less control of the cage density. While in the interactive approach, there is one main interactive approach, which is the one from Lee et al. In this one, the user has to sketch the planes in correspondence you want to refine the cage. This is an interactive method, so rely entirely on the user selection and its accuracy, and requires a big effort for the user to be performed. So another drawback is that cutting plane may induce invalid cross-section, nearly a tiny feature, for example, or high concave region. And once the cut introduces an intersection, it's difficult to solve, as claimed by the authors. So our method aims to solve the main issue of the existing approaches. Our idea is to start from an input shape and its curved skeleton. As I said at the starting of the presentation, the curved skeleton are one type of skeleton that are used as a shape descriptor. So we are picking the semantic from this shape descriptor. So starting from a surface mesh and its curved skeleton, the user has to select the nodes in which you want to bend, want the bending to occur. So you want to refine the cage in correspondence of these nodes. Then there is an automatic processing of the cage. We built symmetric cross-section in correspondence of each node selected by the user. Toward an harmonic field, we will see the detail in the slide after. Then we construct an initial cage connecting the section previously created. This cage is not a final cage because it's inside the model, even if the vertices lies on the surface. Then we inflate this cage, accommodating the character such that there are not self-intersection. So to build our cage, we need to, first of all, do a step of processing in which we construct the guiding field. What means? So we have a surface mesh and its curved skeleton. We construct a volumetric representation of this mesh, such that the surface mesh belongs to the tetrahedral mesh and the curved skeleton as well as a chain of the skeleton. Then we construct an harmonic field in its interior and its surface in this way. So we enforce the direct boundary condition such that the function is evaluated 0 in correspondence of the skeleton and 1 in correspondence of the surface. And then we compute the values in the vertices of this tetrahedral mesh and the values in between, as seen in the close-up. Then for each node selected by the user, we build a small disk close to the points selected by the user, and each sample is projected toward the surface following the gradient of this harmonic field. Each point will be projected in the surface, will lie in the surface of the mesh. Then we constructed quadratic section that best approximate the sample points in the surface. So as it is possible to notice, our code section are not planar as the case of cutting plane. We can see a scenario in this image above where planar cuts will introduce unwanted cut in the model, while harmonic fields always introduce a nice quad section that will not cut entirely the model in between. So regarding cage generation, as I said before, for each point selected by the user, we construct a quad section. Then we connect each quad section belonging to the same branch such that there are no torsion. And we build a polyhedra in correspondence of branching nodes, the one highlighted in green in the image. So the vertices now lie in the surface because they are projected toward the harmonic fields and they stop when they reach the surface, but this is not enough. So another point that I want to touch is the symmetry. As I told before, a symmetry cage, if the model is symmetric, it's a nice feature. And for these reasons, we want to enforce the symmetry of the cross-section if the user required. So this is a result of our cages with and without symmetry enforced. So jumping back to the cage inflation, to the cage construction, the cage built so far has the vertices in the surface of the mesh, so it's not enough to be a proper cage for animation. So what we want to do is to inflate this cage. To do this purpose, we used a mechanism built in nested cages work, which properly inflate a cage given a surface mesh, using our initial cage as cage and our input model as input model. So regarding this step, a problem that is also acknowledged by the authors of the paper is that sometimes in correspondence of tight cage that are not close enough to the surface, it is possible that this method fails to inflate the cage. So for this reason, in our cases, this was happening too often because our cages are, even if the vertices are in the surface, our faces are too far from the shape, the input shape. So we add a pre-inflection step. In this pre-inflection step, we still rely on the harmonic field built so far, and we use a technique to detect how far the faces are from the surface. So basically, we sample the face of the cage, the initial cage. We project each sample following the harmonic fields toward the surface, and then we keep the farthest sample projection from the surface. This is a measure of how far the face is from the input shape. So then we compute a face displacement that gives you a direction for moving the face. And then for each vertex of the cage, we compute a direction which is the normalized, the average of the face displacement of the neighborhood face, and a magnitude which is the length of the largest projection. This is due to the fact that we want to go as far as possible to make the further step properly working. So after this step, we jump back to the cage inflation, the nested cage inflation. Oh, sorry. And we compute the final cage. So coming back to the results, here there is a collection of the results obtained through our method. These are the symmetric cages obtained for nearly symmetric model. These are the results for some of asymmetric models. Then we want to highlight that given the skeleton, the granularity of the skeleton, we are able to build different cages at a different resolution. And then we will see some comparison. So here we can see at left the method shape approximation from Tami et al. And in the right, our method. This is one automatic method, so geometric one. And this is a comparison between the method proposed by Saka et al. And Li et al. The left one is fully automatic, the center one is the interactive one, and the right one is our method. As it's possible to see, our method is comparable to the one obtained in the interactive one, but requiring less effort for the user. So, in conclusion, to sum up, we build a user-assisted method. We combine geometric with semantic constraint. Geometric constraints are automatically handled in the automatic phase of the cage building, while for semantic, we partially rely on the curved skeleton. So the semantic is inferred by the structure of the skeleton. And then for the other part of the semantic, we rely on the user selection. So the user may control the location of the points and the number of density. So both granularity and positioning. So of course, we have some limitation. We are limited to the shape that admit the skeleton representation because it's an input for our method. We have difficulties to build cages for model that has thin surfaces, for example, like the ear of an elephant, which are too thin, and it's not possible to build a proper cross section that represent this area. And well, we may fail to produce a valid cage if the user do not select a sufficient number of bending nodes along the skeleton. And this is a small limitation that occurs few times, but if there are models with narrow tubular feature with high curvature as the image in the bottom, we may fail to produce a valid cage. So as future work, we identify some points that can be touched. So extend, as I told you before, we build a quadratic section with 4 points. We can extend the cage to build n points cross section. Another useful thing would be to construct quad cages. We rely on triangular mesh because in triangular cages because the state of art allows this kind of we're allowing just this kind of cages to be used in the animation pipeline. Then use the mixed line plus surface skeleton to overcome the issue of model with thin surfaces. And well, build the cages for model with self-intersection. This is still a challenging way of build a cage. So that's all for me. Thank you for the attention. And if you have questions, feel free to ask me.
Okay, fantastic. Thank you for a great presentation. So are there any questions? You can, I think there's a question in the chat. No, if you can open it, otherwise I can also read it for you.
Okay, let me.
So actually now there's a second question, but if you look at the first.
Okay, I'm trying to stop. It's a bit, oh, okay, it's already stopped. Okay, so.
The question is, so I don't know if you found the chat, or otherwise I just read it out, might be easier.
Sorry, it's a bit frigid. Okay, maybe stop sharing. Let me.
And I think it's okay. I mean, if you would like to point, okay. But yeah, it's all right. I mean, in any case, you can just answer.
Okay, so the initial procedure needs user interaction. What is the minimum number of bending points you require to guarantee that the construction of the cage? And 2, it is possible to automate the process. So regarding the first one, I think there is not a proper number of bending points that are required, because it really depends on the character and on the position. I mean, if for example, if we look at these no, sorry, I'm not sharing. Let me share again. I was pointing, but you cannot see. Okay. Now you should be able to see the screen. So, for example, if you see this character that is in T-pose, you would not need to insert this point in between the arm. If you don't select anything, it will build by default one cross section at the leaf of the branch of the skeleton. So it will build like a cage that is more similar to a cage used for freeform deformation, I would say. A bit more defined, but it doesn't have all points in between. So it really depends on the shape. If you don't provide enough points, for example, for this one, it would not possible to approximate this ring. You need to have basically more points in the area in which there is a high curvature. So then jumping to the second question. Okay, the second question, it is possible to automate the process. So yes, one part is still fully automatic, while the first part is the only part that requires that requires the user selection. We tried also to fully automate the process in this way. I can share again, maybe. Okay. So we also try to build a fully automatic. Can you see my screen?
Yes.
Okay. We tried also to fully automatize the process. we build an automatic way to select the bending nodes based on local thickness of the skeleton. So basically shape diameter function over the skeleton. So we compute the radius of the maximum sphere embedded in the shape in correspondence of each node of the skeleton. And then we compute the first derivatives, and then we apply a smoothing to basically remove the noise. And then we select all bending points that are on positive local maxima. I can show you the results of these. So basically these are results from automatic placement of the nodes in some of the model we have. The results are not too bad, but it's not, I mean, the good point of our method is that gives to the user the freedom to choose exactly what we want. The fact that the animation is both conditioned by the fact that depends on what the animation would do. If you want to achieve a particular kind of animation and you want to twist, to bend, for example, their arm in a natural way, for example, you cannot bend this part of the arm, but you want it, you should add several points in between. You cannot do it anyway in another way. So it really depends on what the purpose of the animation. So we have it in this, we have a solution for this in the paper, but it's not, I think it's not good enough. I mean, it's a solution for fully automatize the process, but it's not the best way, I think.
Okay, great. Thank you. So I think in the interest of time, maybe we can move on. Just, I guess, one last question, which is like very brief. Is the code open? Have you guys released the code? Or?
Yes, yes, it's open. Should be a repository in which we have the code. Maybe I can also share a link in the Discord channel to.
That would be very useful. Perfect. Okay, thank you very much. Thank you, Sarah, for this great presentation. So let's try again with the speaker for the first paper. So Junzhou, you should be able to try to share your screen right now. I think you're still a co-host.
Thank you, thank you.
Okay, and we can also hear you. So this is a great, great first sign. Okay.
Okay, I will show my screen.
Yes, absolutely. Go ahead. So let's see. Okay, yes, and we can see it. Excellent.
Can you see my screen?
Yes. Yes.
Yeah, thanks. Okay.
Okay, so our second, well, originally supposed to be first, but second paper is Bold's 3D, a 3D Bold descriptor for 6 degrees of freedom pose estimation. And maybe in the interest of mispronouncing everyone's name, I let you name your colleagues. So the presentation will be given by Junzhou. Thank you.
Thank you very much, Mr. Chairman. Good afternoon, ladies and gentlemen. This is Junzhou, and I'm honored to have been invited to speak at this conference. Today, I will present our paper titled Bold 3D, a 3D board descriptor for 6D pose estimation. Here is the outline of this presentation. Before we begin to explore our work, let's take a look at what the object pose estimation is. As depicted in the picture above, what the object 6D pose estimation task is finding the position of a camera relative to an object of interest. Formally speaking, it aims to detect objects and estimate their orientations and translations relative to a canonical frame, including 3 translations coordinates and those 3 rotation coordinates. So imagine you have an object you want to know where exactly it is, and you base a 3D coordinate system around that. 60 pose estimation algorithm takes given image from a camera, and it finds the camera's physical position in relation to the objects, as well as the rotation angle, which is where the name 60 pose estimation comes from. Here are some real scenarios closely related to 60 pose estimation assignment. As a widely studied topic in computer vision and robotics, accurate pose estimations are essential for a variety of applications, such as augmented reality, autonomous driving, and robotic manipulations. In this work, we focus on the robot manipulation application. Specifically, our paper pays attention to 60 pose estimation of mechanical parts, which is a fundamental task and can be further deployed in an automatic picking to assembling system in many industrial enterprises. Actually, in most industrial scenarios, mechanical parts are often present in textureless and high metallic luster form. Moreover, they are often randomly placed in a particular bin together, causing the scenes vertical as well as heavy occlusion between each other. One cannot directly apply traditional region-based 2D descriptors such as shift or surf to distinguish these textureless mechanical parts. So our research question is how to estimate 60 pose of mechanical parts effectively. The problem of object 60 pose estimation has been extensively studied, ranging from imaging-based to 3D point-based approaches. Here are some existing works using feature correspondence and post-closed techniques for object pose estimation. However, those works have some difficulties in handling the dense mechanical parts, such as heavy occlusion, no texture information, internal interference, and so on. Our method is inspired by the work titled Broad Features to Detect Textureless Objects and Model Globally, Match Locally Efficient and Robust 3D Object Recognition. The former literature designed a novel 2D descriptor named board, which is composed of two unique angles built by using the detector midpoints of line segments to detect textureless objects robustly. The latter literature proposed a popular 3D point per feature combined with post-voting scheme to achieve an efficient, stable, and accurate method to find freeform 3D objects in point clouds. However, it's not satisfactory to apply it directly to mechanical parts. Thus, observing that the edge is one of the most important cues for the objects, especially for textureless mechanical parts, we propose to extend the original board feature to the sandy field and combined with point per feature to form a new descriptor. Here is the algorithm pipeline of our paper, which consists of two kernel steps: feature description and pose estimation. In the offline phase, the edge points of the input CD mechanical models are first extracted, and the global model representation is then constructed by both 3D descriptors, which consist of a pair of oriented 3D line segments. These both 3D features are then stacked into a hash table for quickly retrieving. During the online matching phase, the same edge points extraction and downsampling strategy as offline stage is used. The input scenes are represented by a series of both 3D features which are then utilized as a key
Jun? Hello? It seems we can't hear you. I think maybe we're facing some connection issues again, unfortunately. It was going so well. Maybe let's give a couple of minutes to John just to see if he can fix the microphone problem, because at least the screen is still being shared, so there is some hope. Yes, I think it's a good idea to wait a bit. It would be not that great to switch midway. Let's see. So I'm trying to see if at least Jun can hear us, but don't have any response. So maybe.
can you hear me?
Oh, yes, yes. Now you came back.
Okay.
Okay, great.
I'll continue.
So please go ahead. Yes.
Yeah. Okay. During the online matching phase, the same edge points extraction and downsampling strategy as the offline stage is used. As the input scenes and the input scenes are represented by a series of both 3D features which are then utilized as a key to access the hash table. After the correspondence are established and then optimized, the best match is between the input scenes. Oh no, I'm sorry. And the model database are obtained. The final 60 post results are then computed by SVD algorithm. We now show some details of our algorithm. The geometric primitive, which makes up the both 3D descriptor, consists of a pair of oriented 3D line segments, and is formulated as an anti-symmetric 5D vector using different angle and distance, as well as the inner product of two vectors to describe the relationship of two special line segments. During the model representation phase, in order to encode the local geometric structure better, multiple branches of geometrical primitives are aggregated by computing over pairs of neighborhooding 3D line segments. As mentioned above, the board 3D descriptor is designed on the edge of models. Thus, to build the board 3D descriptor, we should extract the edge of the object you are interested in. And to this end, we use the SSI approach, which is proposed by the work titled above. After the edge has been extracted, we utilize the Poisson desk sampling algorithm to simplify the edge point cloud. Next, we established the minimum span tree between these edge points and use the priming algorithm to generate the connection graph to obtain orderly connected line segments. However, we observe that the initial line segments orientation is not satisfactory for model description. So to disambiguate
Oh no, we lost you again. This is very unfortunate. Okay. I don't know if you just want to, so, basically we have this slot for another about 10 minutes or so. If you want to try to fix the connection during that time. Otherwise, unfortunately, I think part of this presentation and the Q&A will have to be on the Discord. It seems there's some serious connection issues, so we might consider just switching to the next paper. I'm sorry about all these problems. It's very difficult to follow. So let's maybe hope that at least with this last paper, it will be a bit better. So I'm sorry, June. We're going to try to switch to the next paper just because it would be difficult for everyone to keep paying attention. Okay, so let me try to make so Yushin, I made you, so Yushin Liu, if you're there, I made you a co-host. So if you can try sharing your screen and I guess unmuting your microphone.
Hello.
Okay, great.
Should I start?
Okay, great. Yes. So thank you. And sorry again for these technical problems. So we'll switch to the last paper in the session. And it's titled Discrete Shell Deformation Driven by Adaptive Sparse Localized Components. The authors are Yuxin Liu, Wuqing Li, Yupan Wang, Yongwei Ni, and Aihua Mao. And Yuxin will be giving the talk.
Okay, thanks for introduction. And hello, everyone. Today, I will share a paper titled Discrete Shell Deformation Driven by Adaptive Sparse Localized Components. And its background is due to many reasons. It is important to reuse time-varying geometries, which consists of a sequence of meshes. And there are two main related works of our methods. The first one is discrete shell. It switches vertex positions to the representations of the edge lengths and the dihedral angles to achieve rotational invariance. And discrete shell deformation by Froelich and Bosch is a typical example-driven deformation by blending the examples. And another related work is sparse localized deformation components proposed by Newman et al. They introduce locality constraint on the PCA basis when analyzing facial animated meshes. And Huang's methods extended the idea to the deformation gradient, and Wang addressed the issues by analyzing edge lengths and dihedral angles. And observing those previous methods or use the same size supports for all components in order to cover large motion regions, or those methods use an oversized support leading to the components covering multiple small regions. As we can see, A shows the components by Wang's method. It covers multiple motion regions. And from B to E are 4 components by our adaptive support strategy, and each covers 1 local region. And the second motivation is that previous methods about the components use blend weights to blend components and to generate new poses. And it is difficult for users to specify proper value of blend weights, and we provide an intuitive way and to directly manipulate the model. And the overview are illustrated as follow. Given a sequence with poses, our approach firstly switches the vertex positions to edge length and dihedral angle. And the adaptive analysis is performed separately. And then we will estimate the support regions of each component during the initialization step of sparse localized decomposition. And then we will have the decomposition optimization. After the optimizations, adaptive sparse localized components for edge lengths and dihedral angles and are obtained, with each of which covers a local region. And users can directly manipulate the vertices, and with the guidance of the components, the editing results are generated. And then with the first step is to have an extraction, and we will extract the edge lengths and dihedral angles of each frame into 2 vectors separately, denoted as LK and phi k. Here is the phi is the dihedral angles, and the length denoted as L. And we will concatenate vectors of the same type into a matrix X. X can represent either edge lengths or dihedral angles. And we will then compute the residual matrix D by subtracting the average of columns of X from each column of X. And the second part is adaptive sparse localized decomposition. And the matrix of the sparse localized components is denoted as C. Here is the matrix C, and J's columns represents the J's component, denoted as CJ. And each entry of a component associates with the length and the angles of one edge. And the sparse localized decomposition of D is then solved by solving this nonlinear optimization. D is the residual matrix, C are components, and W are blending coefficients. The latter term are sparse constraint, and lambda ik are weights used to control the locality and the sparsity. And we solve this optimization by ADMM in 2 main steps. And users will give NC the number of components, and the method will find NC edges with the largest sum of residual as the seed point of each component for initialization. And the second part is to alternatively optimize matrix C and matrix W. And in previous methods, lambda ik is defined as below, and it takes the geodesic distance between 2 points as input as the zeta ik in the blue square. And Dmax is the outside radii of the support of a component. The entry with the distance larger than it will suffer fully sparse constraint. And Dmin is the inner radii of the support, and the entry with the distance smaller than it will suffer no sparse constraint. Indeed, previous methods use the same parameters of Dmin and Dmax, but it is unreasonable to share same local support parameters, and thus we have different radii of support regions for different components. And I will discuss how to determine the radii of each component in the following. And before it, I will first introduce a concept. It is the similarity between two edges. Suppose that edge EI is selected as the seed point of one component. The similarity between EI and another edge EJ is computed as Sij. And how to define Ti and Tj in the formula. And here is the matrix, is a residual matrix D, and Ti and Tj is separately 2 rows of this matrix, and each row of the matrix, residual matrix represents how an edge changes, and we will calculate the motion similarity between two edges by these 2 rows. And the following steps, I will take Samba sequence as examples. As A shows, it is the visualizations of the accumulation of angles changes for all edges. The deeper the color is, the greater the edge changes, and the edge with the greatest changes will be selected as the seed point of a component. And once we have selected an edge, we sort all edges according to their geodesic distance to the selected edge, as shown in the x-axis in figure B. And the y-axis will show the corresponding similarity of the edge to the selected one. And the similarity curve can be obtained as the blue curve. And we then smooth the similarity curve and use a Gaussian kernel to fit the curve. The resulting fitting curve is the orange curve. And since it is a Gaussian kernel, it has a parameter sigma. We choose Dmin is equal to 2 sigma, and Dmax is equal to 4 sigmas. And here is the 2 visualizations of the similarity curve and the fitting curve in the figure C. And the selected edge is emphasized with a thinking line. And we then talk about how to make discrete shell deformation with components. And applying the sparse localized decompositions to lengths and dihedral angles, we can obtain 2 components matrix CL and C5. And the edge lengths and dihedral angles of a new pose can be obtained by specifying 2 sets of blend weights. L star and phi star are the lengths and angles of a new pose. And users can directly drag points to new positions and set new, here is the drag points, and set fixed anchor points on the mesh. Those points will be saved in a handle set H, and the point constraint will then define as below. It pushes the drag points to the desired positions. And involving two pre-computed parameters, BL and B5, the stretching constraint and the blending constraint are shown as below. And it tries to make consistency between the lengths and angles constructed by the unknown vertex positions and the lengths and angles computed by blending the components. And combining all terms together, leading to the following discrete shell energy to solve the vertex positions of the new poles and the blending ways to blend components. And here is some comparisons of editing results. And on the top row from A to D are results by using the components obtained by Wang's methods, and on the bottom row from E to H are edits based on components of our methods, and we can see with the arm raising, the results of Wang's methods become more and more unnatural, while the efforts of the results of our methods remain reasonable. And here are some comparisons of editing results between our methods, Tan's methods and Huang's methods. And A is the rest poses, and B are results of our methods. C are results of Tan's methods, and D are Huang's results of Huang's. And unnatural artifacts appeared in the results of Tan's and Huang's methods due to the large fixed support radii. And here shows another comparisons between the example-driven deformation by Froelich methods and our component-driven methods. On the top, it is a shaking arm data set, which is used to extract components of our methods and to be the examples of the example-based methods. A and D are respos, B and E are the results by example-driven approach, and C and F are results by our component-driven methods. However, the example-driven methods exhibits artifacts as the arm of the women are unreasonably bent as shown in B and E. We guess it is because multiple examples with different poses try to guide this deformation. And here is a video to show the 3D situation of the results. And we show 4 more editing results, and each examples includes 3 images which are separately from left to right are the initial pose, the image download from websites, and the deformation to result by users. And here is a video to show you the 3D results of the previous page. And here are 4 more editing results to show that our approach can achieve large deformation. Thanks. If there are some questions, you can ask me.
Okay, thank you very much. Thank you for the nice presentation. Are there any questions? You can type directly in the chat or raise your hand. So maybe let me start with a question. I think it's really nice work, and the results that you present are very impressive. I was wondering, because you have this sort of more complex pipeline for extracting these localized components, how long does the animation have to be in order to get accurate components? In other words, is there a relation between, for example, the number and the accuracy of the components and the number of frames in the animation?
And indeed, the extraction of components are the time used to extract components are related to many factors, such the number of components, the number of frames, and the edges, the edge numbers of each poses. And we have a very detailed analysis in our papers, and it shows our extractions. It's how to say, we need to achieve the accuracy with more components than previous method. However, as it use adaptive support and the how to say, the occupations we use less occupations than previous methods to achieve similar accuracy.
Mm-hmm. Maybe just to get a sense for those who haven't seen your paper, what is the range of, for example, the number of frames that you have considered and the different complexity of the shapes and the number of components?
How to say, maybe I can let me shows the can you see the papers? And
at the moment we still are seeing your PowerPoint window.
Oh, my PowerPoint. Okay. Indeed.
You can just mention, I guess.
Okay. And as we indeed the let's take the take the ensemble sequence as as the examples, and it achieved the STD error from 0.05 with 20 components, and the errors will minimize to 0.02 with 150 components.
Mm-hmm. Okay.
And I think it's enough for editing.
I guess I was mostly wondering what is, whether there's some limitation on the number of frames that you need in the sequence in order to get reliable components.
And number of frame, I think the number of frame at least, how to say, I think it is no much requirement for the frames, because since we will extract the local motion regions, we can if there is some data on the local region, we can extract them, and we did not rely on how many frames it takes.
I see. Okay. Thank you. Are there any questions? Other questions? Okay, great. Well, if there are no other questions, thank you. Let's thank the other speakers, and I apologize for the technical problems that we had to face with this session. But if you have any questions, and also I communicated privately with Junjo, who promised to upload his presentation on the Discord channel. So at least the slides, but hopefully also the video will get on the Discord channel. So if you have any questions or remarks, you can just try to communicate there directly. So thank you everyone. I guess we're going to take a break now, and let's see, the next session, if I'm not mistaken, starts at 3:30. It's the poster session, and then there's a paper session at 4:15 France time. So thanks everyone again. Thank you.